Swayam Prabha. Digital India. Educated India.
In the last lecture, we got to see the restrictions for the use of Bernoulli's theorem. We saw that if a flow field has certain characteristics, Bernoulli's theorem can be applied between any two points in the domain. However, if the flow field is rotational, then there are some restrictions on the application of Bernoulli's theorem, and we saw that you can still use the constancy of that total head, but you have to consider points on a given streamline, and that followed from the observation that the gradient of the total head was at right angles to the velocity vector or right angles to the streamline vector or streamline direction, which essentially meant that there is some gradient, but along the streamline direction or along the velocity vector there is no gradient. There is no gradient means there is no change. So, that total head does not change as you move along the streamline. Of course, although the rotational irrotational behavior has been restricted, has been lifted, that is, we are looking at a rotational flow field, and hence we are saying that now you can apply Bernoulli's theorem, but as long as you stay within a streamline or as long as you apply it on a streamline. However, the other requirements, that is, the flow field is inviscid. Remember, Bernoulli's derivation started from Euler's equation, the momentum equation without viscous stresses. So, that inviscid assumption comes from there. Then you have the steady assumption, because you saw that the gradient term on the left is equal to the derivative of velocity vector with respect to time is there on the right hand side. So, if that term is there, then the gradient has to be adjusted accordingly as well. So, you cannot just straightforward apply the Bernoulli's theorem the way we are doing at this point. And you saw that the your incompressibility has to be there, because that gradient of p by rho, that thing to write it as, so to write gradient of p by rho, so gradient of p divided by rho as gradient of p by rho, so gradient of bracket p by rho, that incompressibility assumption has been there. So, today I will just like to talk about, because we talked about vorticity and we said that vorticity is a measure of, or is an indicator of whether the flow field is rotational or irrotational. I think a lot of students get a bit confused that why are we suddenly bringing in this curl of the velocity vector. So, today I think I should spend a little bit of time, although this is like a fundamental topic in fluid mechanics, and I was hoping that we can move to like the skin friction drag and boundary layer considerations, but we will delay that by one lecture. So, in today's lecture we will talk about what is this vorticity, why is it connected, or how it is connected to the rotationality of the flow field, how do we even calculate vorticity of a velocity field. And now I will not get into the details of some of these things, for example that okay, so let us get started on the worksheet here, so that way you can see. So, in the last lecture we came to this point where we said gradient of p by rho plus v square by 2, remember capital V square by 2, not the component, okay, the net velocity. So, in an unsteady flow field, if somehow you can keep track of this partial derivative of the total velocity vector, you might still be able to apply these things. Suppose you are doing, you are running, you are computing this thing on a computer, and you can somehow you have these informations from at every time step at every location, then you might be able to incorporate the unsteady behavior as well. But in terms of the application of Bernoulli's theorem in the manner of p plus half rho v square at point 1 equal to p plus half rho v square at point 2. If you want to apply it in that simple form, then your flow field has to satisfy those 4 conditions that we talked about in the last lecture. If the flow field is irrotational, then there is no restriction on point 1 and 2, as long as that inviscid, incompressible and steady behavior is guaranteed. However, I said that if you have rotational behavior or vorticity is non-zero in the flow field, then you cannot just choose any 2 points as 1 and 2. The point 2 and the point 1 should lie on a given streamline, and then this form will again apply. And the reason why it applies in that case was that in a steady flow field with rotational behavior, that is, this is not 0, it can be shown that the direction of these thing is at right angles to the velocity vector or the local streamline direction, which means that the gradient term is at right angles to the local velocity vector direction, which means that the component of gradient, so component of change along the streamline direction is not there, is 0. So, then there is no change in the total head as long as you move along the streamline direction. Okay. So, now what is this thing and how does it come into being? So, we said that this is known as curl. So, I mean this is from mathematics, curl of the velocity field or of the velocity vector, curl of the velocity field. Okay. Keep in mind, so we said that there was when we do the continuity, something called the continuity equation, we will see something like this happening, continuity equation for incompressible flow. We will get this form, which is known as the divergence of the velocity field. This is known as the curl of the velocity field. Now, of course, these are mathematical tools, but what is the physical significance of this curl of the velocity field? And we will see that the curl of the velocity field, and curl is defined as as it is defined in basic vector algebra, vector calculus, in the basic theory of vectors. So, also keep in mind that these things can be expanded depending on the coordinate system that you are using. So, you can be working on a Cartesian coordinate system, you can be working on a cylindrical coordinate system, or you can be working on a spherical coordinate system, and in each of those coordinate systems these expressions can be expanded in different ways. So, we will at this point just stick to Cartesian coordinate system, because the focus of this course is really on the basic ideas of things that are going to come, because as I said in the first lecture or the first few lectures, that these things form part and parcel of aerodynamics, and you will come across these things many times. So, right now my goal is to give you just a flavor of things, not to get into the rigorousness of each individual component. So, the powerful thing about these vector notations are that these are agnostic of the coordinate system. So, you do not need to change, you do not need to change the vector form depending on the coordinate system that you are eventually going to use. So, the vector forms are the same. So, curl is this in any coordinate system, divergence is this in any coordinate system. If you choose the Cartesian coordinate system, then the expansion of this thing will look like what is amenable to the Cartesian system. So, then you can look it up on a basic book on vectors. This can be written as, let me try to be a slightly nicer with these things. So, the way you do that is I j k, then you write the gradient operator, So, you write it like this, follows from your theory of vectors u v w So, you write it in that matrix form. And then you expand it. So, the way to do it is you start with I, you multiply that and subtract that. So, then you go I j k. For j, you have to keep in mind that there will be a negative sign when you do this subtraction. So, then this will be I times, so this term so here you can write plus j times, you have to reverse the order. So, when you do j, you are actually doing this minus this, but then I am changing the negative sign to positive here. So, I am flipping the order of those. So, d du dz minus, you can just look it up on a textbook. So, for k is straightforward, so for k you have this product minus this product. Now, keep in mind that when we look at the deformation and the rotation of a fluid element, you will see that something like this will pop out, okay, and that will connect our angular velocity involved in fluid rotation with vorticity. So, at this point your vorticity is something like, so it just keep track of this expression. So, look at this component in particular. So, that is k times dv dx minus du dy, and we will show that by looking at a fluid element in the x y plane. So, essentially a fluid element will move from say some x 1 y 1 z 1 at t 1 to some x 2 y 2 z 2 at some t 2. Now, this is a solid chunk of fluid that has some volume. Of course, it deforms and it the orientation changes with respect to the initial one, but then we will look at the x y plane, the deformation and the rotation in the x y plane. Similarly, you can look at deformation and rotation and translation, all those things in the y z plane or in the z x plane. It depends, you can choose any particular plane. We will choose the x y plane, and then we will show that the rotation of this fluid element is actually given by half of. So, this is just like looking ahead, so that you know what to expect. So, we will show that the fluid rotation component is something like that, or the angular velocity is like that. So, angular velocity in the in the z direction, because I am looking at the x y projection of the fluid rotation and deformation, it can be shown that the angular velocity in the z direction is given by half of this difference. Similarly, angular velocity in x, angular velocity in y, etc., can, if you write them, you will see that it is just a factor of half difference with the vorticity. So, in vorticity you do not have the half, whereas in angular deformation, not deformation, angular velocity or angular rotation rate, you have the half x term. Okay. So, there is a relationship of that vorticity. If you multiply vorticity by half, you get the angular velocity. So, we will show this, but at this point, just from the definition of these terms, okay, vorticity is the curl of the velocity field. The operator, this operator is defined as this, the velocity vector is defined as this. Then if you work out the curl, then you get this expression. I am saying that it will be shown that the angular, okay, so this is the vorticity, it will be shown that the angular velocity is nothing but half of this thing. Okay, or you can say that the vorticity is 2 times, the other way you can say that vorticity, we haven't shown it yet, but it's quite straightforward. So, I am just writing it down at this point. So, essentially vorticity is 2 times angular velocity. So, this is where this whole idea of rotational flow fields come in. Okay. So, there is some real rotation that is happening, and vorticity is used as a measure of rotation, because it is easy to compute. In a, say, in a computational fluid dynamics kind of setting, at any time point you have velocity throughout the flow field, then you can quite easily calculate this thing, and based on the result of that computation, you can say whether the flow field is vorticity free or it has vorticity. If it has vorticity, you can see from the the relationship that we have written here, if it has vorticity, it essentially means that the individual fluid elements have some angular velocity. Okay. Now, why does that matter? Of course, you see that in a lot of these governing equations, if you have irrotational flow field, that is no vorticity, now you understand vorticity is a measure of the angular velocity of the flow of the fluid particles, or not particles, like fluid parcels, and the relationship, it is not like just vorticity is the measure, vorticity is related to the angular velocity, and you can see that angular velocity is equal to half of the vorticity, or vorticity is twice the angular velocity, and we will show how that happens. So, you see that if the flow field is vorticity free or irrotational, then in Bernoulli's theorem, for example, the application of Bernoulli's theorem, given the other things are holding, you can apply Bernoulli's theorem between any 2 points in the flow field, no need to restrict it to a streamline. We will also see that when we start with this whole aspect of lift on a wing or lift force on an airfoil, we will start with, because see, these things were done, a lot of mathematicians actually were interested in this. I should not say where, this is a area where a lot of applied mathematicians actually work, like the fluid dynamics, aerodynamics. We have a lot of mathematicians who actually work on these things. So, when in the early days of the analysis of lift, drag, etc., we had some mathematicians and theoreticians who argued that if you consider the flow field as inviscid and irrotational, a lot of mathematical simplifications can be obtained and you can actually apply very powerful tools. So, we will see that the velocity potential is something that you can directly apply if your flow field is curl, if there is no curl in the flow field, because curl of a curl of a gradient is 0 by definition. So, if your velocity field is curl free, it means you can express your velocity field as a gradient of something. Okay, so, that is the whole basis on which the potential theory was developed, and we will see that you will see how fascinating this thing is in terms of giving you insight of flow fields and how forces, in particular lift force, is created, because we will see that failure of that classical approach, where you use velocity potentials based on the claim that the flow is inviscid rotational. We will see that there is a grand failure of these classical method, because it fails to give you the drag force, and it was really Prandtl who came up with his boundary layer theory, which eventually made people understand where from that drag force comes from. Okay, so now we will try to look at this angular velocity. Okay, vorticity is 2 times angular velocity, and let us see how that happens. Now, for this we have to draw a small construction. So, let me then just go to a fresh page here, fresh page, very clean. Okay. So, here let us think that we have a fluid package, fluid element. Remember the Lagrangian approach. So, we have a nice fluid element here, element at time t1, and this one moves to some other location at time t2. Of course, you see that it has already deformed with respect to its orientation wise, it has rotated, tilted, it has deformed a little bit, and it has reached a new location at time t2. So, this is at time, let me just try to be a little nicer with these things. So, let us say this is time t1, element at time t2. So, and this is happening in 3 dimensional space, okay, x, y, z, it is moving from one x, y, z coordinate to another x, y, z location, from t1 to t2. It undergoes some translation, rotation, deformation, many things, because fluid as compared to solids, they have, if put under shear forces, it will constantly deform. In fact, interestingly, since it is constantly deforming, the amount of deformation is not of great interest. The rate of deformation is what is of interest. In case of solids, if you apply a shear force, it will deform and then it will resist the deformation and come to like some terminal deformation. But in case of fluids, there is no terminal deformation. As long as the shear stresses are there, it will deform. So, nonetheless, we are interested in the rate of things, not in the absolute deformation of things in case of a fluid. So, now let us look at the, as I said, we will look at the x y projection of this rotation and deformation behavior. Okay, so you can do similar things for the other planes. So, right now we are just looking at the x y plane behavior of rotation and deformation and other things. Okay. So, here as I said that the approach is often very straightforward, and often it is the same approach. If you learn the approach at the initiation of your learning of fluid mechanics, you might have some advantage in applying these things in many places. Okay, so let us think that your A, B, C, D Okay, so let us just say AB and AC. Okay, so it is not, we do not need to worry about this location D, and you will understand why. So, let me just stay with the convention. So, AB and AC. Now, what is special about AB and AC? These are at the time t is equal to 0, you have chosen a set of mutually perpendicular lines. So, not this one. Okay. So, this is mutually perpendicular at time t is equal to 0. This length, you can think of this length as, okay, first of all let us put the velocities. Say at point A, the velocity here is u, and the velocity in this direction is v. This length, let us say this length of this side, remember it is a differential element, and you need to get familiar with this approach. You will see that this approach is common in fluid mechanics, just like you did calculus problems, in 11, 12 and bit of the first year as well. So, you have to put the problem or set the problem in terms of the dx, dt, d theta and integrate or something. Similarly, here you are setting up the problem, and it depends on the level of incorporation of real things in it. So, you can incorporate a lot of details, or you can say I am going to incorporate only the the big picture things, not the minute details. So, your model will be different, but nonetheless it will still capture some flavor of what is happening. So, in this case this is dx and this is dy. So, I am saying that let us say that my velocity here, remember velocity here we can write in with Taylor series expansion, v plus rate of change of v with respect to x into the extent of this change in x. Okay, so, that is the velocity v velocity at the point C. Similarly, the u velocity at the point B is u plus dou u dou y. So, with respect to y. So, I am changing my y. So, u plus the rate of change of u with respect to y multiplied by the extent through. So, this is the rate at which u changes with y, and this is the amount of change in y. So, that gives you the new u velocity. Now, let us assume that, so this is what is happening at time t is equal to t1. At the instant time t2, so here we are looking at the 3 dimensional isometric view or something like that. Here we are just looking at the slice on the xy plane. So, what is happening here is A has moved say to this point. Now, let us still draw the lines that are parallel to the initial orientation. Okay. And so, the point A has moved to this location A, or we can call it A prime, but you know what we are talking about. So, let us just stick to A. Now, my point C, remember C is, so point A has a vertical velocity of v, whereas point C has a vertical velocity of v plus something. So, my point C actually, instead of lying on this horizontal line, will come to this location, because the v's, so the v velocity at point A and the v velocity at point C are different. So, the point C will come here. Similarly, point B, see the u velocity of point A is u. So, the u component of velocity at point A is u, whereas the u component of velocity at point B is u plus something. So, here also my point B will have shifted with respect to my. So, my point B has come here. So, now you see that my fluid element has deformed, okay, from a nice rectangular or very sharp corner, 90-degree corner cross section. You see that it has deformed depending on the velocity gradients. Okay. It can deform like that, it can deform in some other way, it can also not deform, but just rotate, but nonetheless in a general sense this is a possibility. So, then what is, let me change the color. Okay, so, what is this distance and what is this distance? Just trying to be a little bit. Okay, so, what is that distance and what is this distance? We are interested in those distances because we are really interested in these angles, because these angles can be given as the tan of this by this. This angle can be given as tan of this by this. Okay, so, now this distance is, so now think of it, this u, the vertical velocity is u, the vertical velocity is v, and vertical velocity here is v plus something. So, then what is the difference between the vertical location of A and C? It will be the difference in vertical velocity multiplied by the time. So, this vertical velocity is v, this vertical velocity is v plus something. So, that plus something into the time through which that difference of velocity operates is this new distance. So, then this line is dou v dou x times dou dx into dt. Okay. So, the relative shift of C with respect to the dotted line is given by dv dou v dou x times dx into dt. So, essentially the difference of vertical velocity between the points A and C, which is dou v dou x times dx, and multiplied by the time interval between these two snapshots. Okay. So, this is at time t and this is at time t plus del t. Okay. So, we get that this line C, say C C bar, again you can just name whatever you want, say C C bar, and let us call it B B bar. Now, what is B B bar? Similar to, so now look at the difference between the u velocities. So, difference is dou u dou y times dy, and if you let this thing move through a time interval of dt, then the relative shift will be given by, so this length will be given by this difference into the time through which that difference gets a chance to operate, dy times dt. Okay. So, like setting up this problem is important. Once you have set up this problem, then we have to apply some definitions, and then you will see a lot of things fall out. Now, AC can be written as to be equal to dx, and this one can be written to be equal to dy. Okay. So, this is dy and this is dx. So, we say these are the same. Now, of course, some of you will start wondering that if the horizontal velocity of A is u and the horizontal velocity of C is u plus dou u dou x times dx, then there should be some change in that dx as well. Similarly, if the v velocity at point A and the v velocity at point B are different, then also instead of that this line being dy, it should be dy plus something, depending on what is the relative speed between A and B in the vertical direction. But you can work it out given the limit dt tends to 0, it can be shown that that thing can be written as dx and dy eventually. Okay. You can work it out, that is the new dx and the new dy in the limit time dt tends to 0, it will come back to dx and dy. Okay. So, at this point then we have c c prime is this term, a c prime is dx, a b prime is dy, and b prime b is dou u dou y dy dt. Now, we will define angular velocity as, see, this line has moved in a counterclockwise direction. This line has moved in a clockwise direction. So, the way we define rotation is we take the mean of the clockwise rotation of these mutually perpendicular lines. So, we take the rotation as the mean rotation of two lines that were initially orthogonal or perpendicular to each other. So, you take these lines AC and AB and look at the rotation of each of them, because see, if both of them rotate anti-clockwise by the same amount, half of the rotation of both of them added together would give you the rotation of that element. Problem is when they are rotating in different amounts. So, there also we take half of the rotation of AC plus the rotation of AB, of course, taking the signs of the direction of rotations accordingly. So, what I am saying is, if you take half of the rotation of AC plus half of the rotation of AB, or half of the bracket summation of the rotation of AC and AB, and if both of them are rotating through the same amount in the same direction, then it is almost like the solid body rotation. So, the mean of the rotation of this and this will actually be same as the amount of rotation of the solid counterpart. But here in fluids, in most cases, in fact, keeping the orientation 90 will be an exception. In most cases, these mutually perpendicular lines, well, these lines that are initially perpendicular to each other will rotate by different amounts, and then what we will say is that omega z is equal to half of so what is the rotation of this line AC? It is dV by dx dt divided by dx. Okay, so that is this angle. This side by this side is tan of this angle, but that angle is small. So, you can just say that the angle itself is the ratio of these two. So, this is this angle divided by, okay, you can just subtract du dy dt divided by dy. So, now I am dividing this by this, which kind of gives me this angle. Okay, let me write this thing later, this half thing. Okay, so this difference really gives you say this is theta 1, this is theta 2. So, this one gives you theta 1 minus theta 2. So, I am taking anti-clockwise as positive. Okay. So, then your angular velocity is given as half of theta 1 minus theta 2 divided by the time. Okay. So, here we will have dv dx into dx dt. So, that was the this thing. When I divide it by dx, I get this angle theta 1. Similarly, I get, so remember these are in other opposite directions, that is the change in angle divided by dt. Okay, so, that is the angular velocity. So, change in theta over time, and this comes to be okay. So, you see that the z component of the angular velocity. So, angular velocity is a vector composed of w x, w y, w z in the I, j, k directions, and we see that the z component of that angular velocity is given by this expression. Okay. In fact, you can work it out that if this turned by theta 1 this direction, this one also turned by theta 1 this direction, then this approach would give you omega z is equal to theta 1 by dt, because then it will be theta 1 minus of minus theta 1. So, 2 theta 1. Okay. Anyway, so you can just follow this one. So, you get that the angular velocity component in the z direction is this, and now if you remember or if you go back to our vorticity component in the z direction, see how these two are connected. Okay, let me just write this one w z Okay, so this is how it is defined. Okay, so clockwise rotation, in this case we have set anti-clockwise rotation as positive, and you have to take the average of the rotation of the two perpendicular lines, well, two lines that were initially perpendicular to each other. Okay. So, that is how it is defined, and here you get this component is half of okay. So, your omega z is given by half of that, and if you see that your eta z, the z component of your vorticity is given by okay. So, then what do you see? What is the relationship between vorticity and the angular velocity? See, angular velocity is a very physical thing. Okay, we started with the fluid element, we looked at it after a small interval of time dt, a set of mutually orthogonal lines at time t initial moved and deformed to at the new location. By definition, we say that the relators define that the rotation of this, and you see the definition is such that if this rotated as a solid body, then see both the lines would have rotated by theta. If it rotated as solid body, then you would get net rotation of 2 theta divided by 2. So, rotation of theta. So, I think that is what has been aimed in setting up the definition of this rotation of the fluid. So, now we see that the rotation and the vorticity are connected. So, if you can show that the vorticity is 0, it means that your individual elements are not rotating. Okay. So, there is no net rotation. So, you can still have deformation, just a second. Okay, so let me just write this thing. So, if you now look at all the other components, so here I looked at the xy plane. So, I got the z component of angular velocity and I am comparing with the z component of vorticity. Similarly, I can get the so here I got the z component, here I would get the y component, here I would get the x component of vorticity, and if I look at those components of rotation as well, then I can relate vorticity with this as curl is equal to 2 times angular velocity. It means that I have to multiply this by 2 to get this. Okay, 2 times half into this is equal to 1 into this. Okay, so that is why I am saying multiply angular velocity by 2 to get the curl. Okay, so this is, so if you can quickly calculate the curl of a velocity field, and curl can be easily calculated by this definition, then you can actually calculate the rotation of the fluid element along various slices or various x, y, z planes. Now, keep in mind that a fluid may deform, but not rotate. So, if it happens that the clockwise or the anticlockwise rotation of this balances out the anticlockwise rotation of this, then overall this element is not rotating, but it is still deforming. So, while rotation is given as the difference of these things like this, deformation would be theta 1 plus theta 2, which is, so when we say deformation, so in this kind of analysis we are interested in both the deformation and the rotation. It can so happen that the two lines rotate in opposite directions by the same amount, so your net rotation is not there. On the other hand, deformation in the xy plane, and actually this is the rate of deformation, is given by this angle plus this angle divided by dt. So, that becomes dv dx dx dt by dx, same thing as rotation, but with a plus sign in between, du dy times dy times dt divided by dy. So, essentially this is theta 1, this is theta 2, and we are adding them, and then we are dividing by dt. So, essentially then this becomes dv dx plus du dy. Okay, so, this is the rate of deformation of this fluid element in the xy plane, and it will be shown. So, this is the rate of deformation in the xy plane, and it will be shown that something called shear stress, and we will see why that xy and yx are the same, is will relate to, so the stress strain relationship. So, we got the the shear strain rate, and so rate of deformation is connected to the shearing force, and we will show this thing in some subsequent lecture. That is, so this is the rate of shear deformation, and this is the shear stress that causes that shear deformation, and we see that there is a proportionality between the two, and the constant of proportionality is the viscosity. We will also see, and what does these things mean? This just means that this is the tangential force on the surface whose normal is in the x direction, where the shear force in itself is in the y direction. So, these kind of tangential forces or stresses are defined in with two subscripts. The first subscript, so we will talk about this, when we talk about the stress tensor, we will talk about this one, but at this point it is I would like to mention that this is the first subscript tells you on which plane this surface stress is acting on. Remember, for this we are talking about the stress that is parallel to the surface. So, then there are two directions of importance. One is the direction of the plane on which it is acting. So, the first subscript somehow gives you the plane on which this shear force is acting, and now if you think of a plane on which a tangential force is acting. So, the plane is now defined, but you still have the direction of the force itself. Okay. So, when you have a surface, so now the surface is given. If your first subscript is given, that means your surface is given, orientation of the surface is given, but on a given surface, if I tell you that there is a tangential force on the surface, you still need to tell me what is the direction of the tangential force acting on that surface. So, the first subscript here tells you which surface, and the second subscript here tells you which direction on that surface. We will see that x y and y x, these shear stresses will be the same, and there is a little bit of a small diagram like this that we have to draw, that will give us this notion that the shear force on the x surface in the y direction is same as shear force on the y surface in the x direction, and either of them is proportional to the deformation in the x y plane, and the constant of proportionality between them is the viscosity. Okay. So, now one more thing that I would like to start in this presentation in this session, but I think this will spill to the next one, is the notion or the equation of the streamline. So, remember we talked about streamline in the last lecture, and we said that the Bernoulli's theorem, or that P plus half rho u square thing is constant along a streamline, if the flow field is rotational. Of course, if the flow field is irrotational, it is it is constant between any 2 points. So, on the streamline also it is constant, but if the flow field is rotational, then it is not constant between any 2 random points, but as long as the points lie on the same streamline, your P plus half rho u square is constant. Now, while we talked about streamline, we talked about that PIV experiment where you get the velocity vectors at different points, and then you join, you draw the curves. Remember, streamlines are hypothetical curves, there is nothing called a streamline in a flow field. On the other hand, there are more physical lines in a flow field. For example, there is something called path line. In fact, if you see a smoke flow visualization experiment, you have a tube and some smoke is being released, and then you have, okay, so this one again there is some nuance between path line and streak line. So, there are different lines that we talk about, it's just something that it's good to know. Streamline, then we have the path line, and these are something that will be relevant when you run experiments. So, you have a line of, say, in a liquid flow experiment. Remember that the incompressible aerodynamics is very similar to hydrodynamics, because the liquid water also exhibits its incompressible behavior. So, you will see a lot of these airfoil experiments in water and rendered visible by your hydrogen bubbles. So, you have hydrogen bubble, you have electric wire that is generating hydrogen bubbles in water, and the water is flowing past the wire, it is stripping off the hydrogen bubbles, and the bubbles are flowing over, say, your geometry, your airfoil or your cylinder, and it is rendering the flow field visible, just like your PIV thing. So, we said in PIV you add some particles in the flow field, you shine a laser, particles become visible, and then you can do some post processing to figure out velocities, etc. In in hydrodynamics, there is the convenience of generating hydrogen bubbles. So, you have a wire, maybe it's you have to see, it depends on, like, you can have a tungsten wire, the diameter of the wire in some way influences the size of these hydrogen bubbles. So, you have a wire that is connected to a battery, and we have an anode cathode arrangement, and bubbles of hydrogen forms on these wire due to hydroelectrolysis of water, and you might need to add some acid or some kind of impurity to the water to make it conductive. But nonetheless, you have these bubbles, and the bubbles are stripped off and they follow the flow. You essentially get a way of flow visualization, and YouTube has a lot of these kind of very interesting flow visualizations over airfoils at various angles of attack, etc., that you should see on your own. I have given you, like that, the National Committee for Fluid Mechanics films set of that 25 to 30 videos and topics. You should do that. In the next class, we will start with quickly defining streamline, path line, and as I say, streak line. There is also something called timeline. Again, just a few things that are of convenience to us, and we will see that in a steady flow, streamline, path line and streak line all more or less mean the same thing, because they collapse onto each other for a steady flow field where nothing is changing with respect to time. So, in the next lecture, we will start with a basic definition of these or basic idea of these lines, because it is useful for experimental, when you run an experiment and you want to interpret what is happening, sometimes it is important to know because you have all these particle lines or the path line, etc. So, we will talk about it, and then we will derive the equation for the streamline. And because we talked about the fact that your Bernoulli's head is constant along the streamline in a rotational flow field. So, of course, given it is inviscid, incompressible and steady. So, we will see a way of deriving the streamline equation, and I think it will help you to derive the lines for other contours as well. Okay, so we will I will see you guys in the next lecture, and we will get into once we do this, we will start working on the boundary layer aspect of flow, because to understand drag over airfoils, it is another crucial building block. Once we know flow field, pressure, velocity and the boundary layer element, then we are in a position to talk about flow separation drag, shear force drag, etc. So, till then, thank you for your attention. See you next time.